Okay, so in this video I'm going to show you just a bare bones basics how-to with mathematical induction. Mathematical induction is just a way that we go about proving that certain mathematical properties are true. Definitely want to save these for the special cases. So one situation where you need to use mathematical induction would definitely be with proving series like these ones here. And the necessary steps in proving a series is true inductively is first the base case, which you have to show that the statement's true for the first term. In other words, if we were to look at this problem, right, this little part right here, all we need to do is show that we will get the first term, which is 2, if we plug a 1 in here for n on the other side of the equation, which will look something like this. So notice here, to get our 2, which is this 2 right here, we just need to show it's true, so we're just going to put a 1 right here and a 1 right in there, which is 1 squared plus 1, and 1 squared plus 1 is 2, so we've successfully proven that. Pretty simple. Moving on to the second case here, the second part here is assume that n equals k is true. So this is somewhere along in the series. Assume that this formula will work for some other term in the series, and we're assuming it's the k term, somewhere in between, the first term and the n term, in other words. Pretty simple strategy here. All we really have to do here is just replace n with k, and when we're talking about n with k, we're talking about that series right up above there. So as you can see here, I'm just copied down the same series that we had up here, 2 plus 4 plus 6 plus all the way out to, instead of going to 2n, the k term in that series would just be 2 times whatever value k was, whether it be the 30th term, the 50th term, the 500th term. And what we're doing with this assumption is we're going to assume that if we were to do this series up until that point, it would just be equal to that same number squared plus that number, k squared plus k. And now we have successfully done step 2. Now the fun part, step 3. Now we have to set out to prove that n equals k plus 1 is true. What that is referring to is the term after the k term. So picture all the terms all the way out to k, like so. 2 plus 4 plus 6 plus all the way out to 2k. Now if k was, say, 30, then we would have the 30th term right there of 60, 2 times 30. Well, what would the k plus 1 term be? In other words, what would the 31st term look like? Well, it'd look like 31 times 2, which would give us 62. So how does that look algebraically? It's going to look something like this. 2 times, instead of k, we're going to do 2 times k plus 1. Now, we're trying to prove that this is going to be equal to something. What we're trying to prove is that this will be equal to is if we were to put the k plus 1 term in there for n right up here for n squared and in there for n, so it looks something like this, where now we have k plus 1 squared plus k plus 1. All I'm really doing here is replacing this n with k plus 1 and replacing this n with k plus 1. So now what we're setting out to do is to show that both sides are equal to each other. So just like when we were proving trig identities, what I don't want you to do is move things from one side of the equal sign to the other. Leave everything in place, and then we're just going to simplify both sides until we get them to say the same thing. So pretty much all this involves on the right side is just simply getting rid of your parentheses and combining like terms. So the first thing we're going to do with that k plus 1 squared right here is let's go ahead and square that. So as you can see here with k plus 1 squared, we're going to end up with k squared plus 2k plus 1. So all we saw here with the k plus 1 squared is we got this quantity right there. And then with this k plus 1 here, that just got copied down right there since we didn't do anything with it. Great, so now what we need to do now is just simply combine our like terms. And so we arrive here at k squared plus 3k plus 2, combining 2k and k and combining 1 and 1. Now what about the left side? The move that needs to happen every single time here to make the left side match the right side is notice that you wrote a series all the way out to the k term, just like that, and then we added the k plus 1 term. Well, earlier in our work here, we made a very, very important assumption here. If we went out to k, then it would have to be equal to this value right here, k squared plus k. So what we're going to do here is we're going to replace the series that we had all the way up to the k term with k squared plus k. And that move is going to happen every single time we're dealing with these particular kinds of series. And now our next move is looking at this stuff that was still left over from the left side of the equal sign, which is this 2 times k plus 1. Let's go ahead and clean this up by using the distributive property. So now we're looking at 2k plus 2, and we're going to be adding that in. So now looking at what we have left here, now what we need to do is just combine our like terms there. And there you have it. We have k squared plus 3k plus 2 on that side, k squared plus 3k plus 2 on that side, a finished induction proof. Let's do this one more time with another example. Let's prove that the sum of the first n positive integers is equal to n times n plus 1 divided by 2. Notice one thing that they did not do here is provide us with an equation with a series to go along with it. When that happens, just take a second and just translate it into an equation that fits the profile here. I think it would look something like this, right? The sum of the first n positive integers, so 1 plus 2 plus 3 all the way out to some number n, would be equal to n times n plus 1 divided by 2. So to prove that this is true inductively, the first thing that we have to do is prove the base case that n equals 1 is true. So all we need to do here is show that the n times n plus 1 divided by 2, when we substitute a 1 in here and here, let's see if when we plug that in there we end up getting a 1 out of this. So as you can see here, when we get plug in a 1 there, here and here, we do the math on that, we end up with a 1, which matches the first term right here of 1. Okay, so let's look at the second part, the assumption here. If we assume that n equals k is true, then just replace n with k, and we end up with something that looks like this. So make sure you have that part written down and when you're doing step 2. Because remember, we saw in the last problem, writing this out here in its entirety will pay off when we get to step 3. Okay, so now step 3. N equals k plus 1 is true. So like with the last one here, write them all out to the k term, which really just involves you just copying down what you wrote for step 2, at least the left side of the equal sign. So we go on ahead and we write that out to k, but then we got to write the term right after the k term, which is k plus 1. Not very exciting here, just write another plus sign and drop in a k plus 1. Now what's this supposed to be equal to? What we have to do now is substitute substitute a k plus 1 in there. And then we need to substitute a k plus 1 right in here. Now if we do this carefully, notice we're going to have k plus 1 plus 1. So wouldn't that just end up being k plus 2? And then if we have k, those two things put together, don't forget we still have the 2 in the denominator. Excellent. Now to prove that these two things are equal, we just work both sides until we get them to match. One thing that you can do, it doesn't matter which side you work here first, but if you work the left side, remember that important assumption that we made back in step 2. And that was the assumption that everything right up here until we get to k, we assumed that that was going to be equal to this right here. So just as before, let's substitute k times k plus 1 over 2 in for that series only up until k, giving us something like this. And then don't forget the k plus 1 term going in here. So there's our k plus 1. Now let's just stick with this side here. If we were to keep on looking at this side here, because we have k plus 1 sitting right here, now with a fraction that we just put in here with the substitution, kind of forces our hand here a little bit and forces us to kind of drop a 1 under there. And now we got to add these two things together here. So if we're going to add those two together, one thing that we're going to need is a common denominator. To get a common denominator here, notice that all we have to do is multiply both the numerator and the denominator there by 2. Now from here, what we're going to do next is just clean up each one of these numerators and at the same time write one fraction. So let's do distributive property here. Notice we're going to have k squared plus k. Doing the distributive property here, we're going to have 2k plus 2. So now that we have k squared plus k plus 2k plus 2 over 2, we can combine our like terms right there in the middle, combine k with 2k, giving us now k squared plus 3k plus 2 over 2. It's about as far as we're going to take it here. Now let's look at the other side and see if we can get to match. Obviously with the numerator up there, we're probably going to want to FOIL that, right? So let's continue to FOIL it. And just by that foiling right there, that was enough for us to see that both these two sides are indeed the same, so we have successfully proven it.